Okay, so in this lecture we will take up the question of Laplace transforms of various important signals, that is time signals x of t, and find out the abscissa of convergence for this. For each of this in a routine fashion. Okay, we will do that. We will take up some important signals like del of t, then u of t, and r of t, and so on and so forth. Okay, before that, let us look at the condition for existence of Laplace transform. So this condition is usually stated as x of t should be of exponential order. In other words, f of t can grow with positive t more than an exponent of some value. In other words, there exists some sigma. This is a real value such that limit as t goes to infinity then e to the minus sigma t times x of t goes to 0. Okay, so this is the main thing we need to consider. Like you take any function, that function grows with the positive t that we have seen in the last lecture. Let's say e to the 2t. When t goes to infinity, and this guy also goes to infinity, therefore what we do is we will take this e to the 2t and multiply by e to the minus sigma t, such that for these two guys, if you allow limit t goes to infinity, then this will go to 0. Okay, so therefore this x of t should be of exponential order. That's what we mean, exponential order. Okay, now we will take up Laplace transformation of important functions of time. Okay, to start with, let x of t is equal to del of t. Okay, so what is this? An impulse at the origin. So if you try to plot it, then it looks like this, del of t, and this is t, and here t equals 0. Okay, now what is a Fourier transform? Laplace transform. Laplace transform is denoted by capital X and small s is equal to integral of, now the limit is 0 to infinity, and x of t e to the minus st times dt. Now what is del of t here? X of t here, del of t times e to the minus st times dt, and the limit is 0 to infinity. Now you apply the multiplication property of your del of t. Okay, so this del of t times e to the minus st is equivalent to del of t times the value of this e to the st at t equals 0. Therefore, del of t times e to the 0 is again del of t. Okay, so therefore this is like you are having impulse. That means the impulse is starting from like this. It's a finite width, and this point is 0 minus, and this point is 0 plus. Therefore you start your integration from 0 minus. So 0 minus to infinity, then del of t, anyway this value is 1 and dt, and again if you see this is precisely the definition of an impulse function, and area under the impulse function is equal to 1. So, therefore, this is 1. So, your x of s is equal to 1. Okay. Therefore, the value of this integral is equal to 1. So, del of t has a Laplace transformation equal to 1, just like in the case of Fourier transform. Even in the Fourier transform also x of j omega is equal to 1. Here also the same case. As far as the abscissa of convergence is concerned, it does not matter what value of s or what is the real part of s. It can take any value. Okay, the sigma can be any value. It will always be 1. So, it does not depend upon the real part of s. So, we do not have any particular restriction on the real value of s. Now, let us consider another example. X of t is equal to u of t. So, the Laplace transform is equal to integral of 0 minus to infinity x of t e to the minus st dt. This is a definition. So, x of t is equal to u of t. U of t has a value 1. Therefore, e to the minus st times dt, and the limit is 0 minus to infinity. In this case, you can start 0 also, no problem. After all, it is a u of t. Okay. This one you can put either 0 minus or 0 plus, no difference. So, this is e to the minus st divided by minus s, and the limit is 0 to infinity. Now, in this range of integration, u of t happens to be equal to 1. Therefore, you can write this x of t as it is. This is 1. So, e to the minus st, and now the upper limit is infinity. If you substitute e to the minus s times infinity minus e to the 0 divided by minus s. Okay. So, the upper limit is e to the power minus infinity times s. So, if the real value of s is greater than 0, in this one, this s is greater than 0, then this guy goes to a finite value, otherwise it will go to infinite value. Then you have say, let us say minus a small real value. What is s? S is equal to sigma plus j omega, right? Now, forget about this j omega. So, e to the minus s times infinity minus 1 divided by minus s. Now, in this one, in the exponent, if you take alone, e to the minus of sigma plus j omega times infinity. Now, e to the minus sigma times infinity times e to the minus j omega times infinity. Now, this is always oscillates between plus or minus 1. Why? Because e to the j theta is becomes cos of j infinity, cos infinity plus or minus, cos of infinity minus j times sin of infinity, right. So, whatever the argument you put does not matter. Okay. Like if you recall, cos 0 is same as cos of 360 degree, and this is same as cos of 720 degree, and so on and so forth. Whatever the value you substitute for this cos, then the value is always oscillates between plus 1 or minus 1, that is the maximum value it can take or minimum value it can take. So, this guy is not a problem. Not a problem, but here there is a problem. What is the problem? If sigma is greater than 0, no issues. Let us say sigma is equal to 0.1 or positive value. When I say sigma greater than 0, that means what? Positive value. If it takes positive value, then e to the minus positive value multiplied by infinity. So, that is e to the minus of infinity. So, e to the minus infinity, what is the value? 0. But in case if sigma is less than 0, then what will happen? that means it is negative. Therefore e to the minus of negative times infinity, then negative times negative positive, so e to the positive value divided by again multiply by positive value, so plus infinity. So e to the plus infinity is equal to infinity, so it will not converge. Therefore in order to converge this relation to a finite value, what is the condition? The sigma should be positive, it should be greater than 0. Sigma is greater than 0 means what? Your real part of S must be greater than 0. That's it. That's what we are trying to say here. So as long as sigma is positive, that is sigma is greater than 0, then real part of S is greater than 0. That means as long as sigma is positive, when t goes to infinity, the magnitude of this function, which is governed by e to the minus sigma t, goes to 0. Okay. So after all, e to the minus sigma plus j omega t, then j omega times t. Okay. So this we can write e to the minus sigma t times e to the minus j omega t. So therefore the magnitude of this guy is always 1. It doesn't matter whatever the value you substitute for t. Okay. You substitute any value, its magnitude is always equal to 1. But the magnitude of this e to the minus sigma t depends upon sigma as well as t. So as long as sigma is greater than 0, if I put like this, what is the meaning of this? Sigma is positive, and t goes to infinity, then e to the minus sigma t goes to 0. Therefore at the upper limit we make sure that this e to the minus st goes to 0 by taking when limit t goes to infinity. So this is the condition we need to find out. So this happens only if real part of S is greater than 0. Okay. So in that case, e to the minus st divided by minus s, and the limit is 0 to infinity. So e to the minus infinity minus e to the 0 divided by minus s. So this is 1 over s. I mean 0 minus 1 minus s. This is minus 1 by minus s is equal to 1 over s. Minus 0 minus 1 divided by minus s. Therefore the Laplace transform of u of t is 1 over s, provided the real part of s is greater than 0. That means sigma is greater than 0. So what is the region of convergence? The entire right half of the S-plane. Okay. So that means the integral will converge only if you take that particular condition. What is that particular condition? Real part of S should be greater than 0. Otherwise the integration will not converge. And that means the abscess of convergence for this okay, happens to be 0, which is minimum value of the real part of S that we should have. Therefore u of t, if you take Laplace transform, 1 over s, and real part of s is greater than 0. Therefore this Laplace transform is valid as long as real part of s is greater than 0. That means sigma c is greater than 0. See, this is very important condition. That's why I am giving more stress on this. Otherwise it will lead to a lot of confusion. Greater than 0. Okay, so the real part of s must be some positive value which is larger than 0, of course. So these are the two important functions, okay, for which we have found out the Laplace transformation. Therefore, if you find the region of convergence, then this is sigma and this is omega. So sigma is greater than 0. That means what? This is the region of convergence for your u of t, ROC. So the entire right half S plane, that is your region of convergence. Okay. Now let's move on to the next example. So x of t is equal to e to the minus alpha t times u of t. Now by definition, x of s is equal to 0 to infinity e to the minus alpha t times u of t times e to the minus st and dt. Anyway, from 0 to 1 this is equal to 1. So rearrange the integration. You put 0 minus always for the safer side. E to the minus alpha plus s times t and dt. Okay. Again this is equal to e to the minus of alpha plus s times t divided by minus of alpha plus s, and the limit is 0 minus to infinity. Okay. Now once again we would like to make the integral converge at t equals infinity. Okay, that means what? By making sure that the real part of alpha plus s is positive number. Real part of alpha plus s must be greater than 0. If I write greater than 0, what does it mean? It means a positive number, a non-negative number, that's it. So therefore alpha plus sigma must be greater than 0. That means what? Sigma is greater than minus alpha. Okay. So at the upper limit, the real part of s plus alpha is greater than 0. So at t goes to infinity, then what happens? E to the minus of alpha plus sigma plus j omega t, maybe I will write down here. See, e to the minus alpha plus s plus t divided by minus of alpha plus s, and the limit is 0 to infinity, 0 minus. Now what does it mean? E to the minus of alpha plus sigma plus j omega times t, and the limit is 0 minus to infinity. But this we can rearrange as e to the minus of alpha plus sigma times t times e to the minus j omega t whole divided by minus of alpha plus s, and the limit is 0 minus to infinity. Now you substitute the upper limit, then what will happen? What will you get? E to the minus alpha plus sigma times infinity times e to the minus j omega times infinity minus e to the 0 whole divided by minus of alpha plus s. Now this portion is not a problem. This is equal to 1, and this also not a problem. This also equal to 1, because e to the j theta is equal to cos theta plus j sin theta. I already told you, but this guy is a problem. Okay, and this should be non-negative. If it is negative, then what will happen? Already have one more negative, and this negative both will positive. Positive times infinity, positive infinity, e power infinity becomes infinity, so therefore it will not converge. So you always make sure that alpha plus sigma is always positive. That means what? Sigma is greater than minus alpha. So in the plot, if you put like this, this is my sigma, then let's say this is my alpha minus alpha. Okay, so this point, therefore my region of convergence will be like this. Okay, therefore this expression simplifies to 0 minus e power 0 is 1 divided by minus of alpha plus s. Minus minus will get cancelled, so alpha plus s, that's it. Okay, therefore e to the minus alpha t times u of t, if you take Laplace transform, then it is 1 over s plus a, and the real part of s is greater than minus alpha. Okay, so always you should mention the ROC. So this is my ROC, region of convergence. Okay, so here we are taking alpha to be real in this case. Okay, here alpha is real. Even if you have taken e to the minus zt, where z is a complex, we can go through the same arguments, same analysis. Okay, then finally let's say e to the power of minus zt times u of t, then the Laplace transform divided by 1 plus s plus z. But now this ROC will be real part of s must be greater than real part of z, that's it. You can prove this minus of real part of z. Okay, so that's it. So alpha need not be real, it can be complex also. Okay, it could be even a complex number. Even if it is complex, the same relation should be valid, but only the ROC should changes. You can straight away you can substitute. See, integral of 0 to infinity e to the minus zt times e to the minus st times dt, then it is e to the minus of z plus s and t and dt. Okay, now 0 to infinity, then this guy should be non-negative, otherwise the integration will not converge. That is z plus s must be greater than 0. Why are we always talking about real part? Because imaginary part is not a problem. Why? Because e to the z plus s times t, you can write e to the x plus jy, let us say z equal to x plus jy, x plus jy, s is sigma plus j omega multiply by t. Now in this we need to consider only x times t times e to the sigma t and e to the j times yt and e to the times j times omega t. See, this imaginary part no need to consider. No need to consider. Why? Always we will be more concerned about the real part. The reason is, whatever the value substitute for t, either you substitute t equal to infinity or t is equal to minus infinity, it does not matter, because the magnitude of these two guys will always be 1. It will not diverge, it always converges to 1, but that is not the case in these two guys. Therefore, that is why we always talk about the real part of a complex number or real part of a complex function, right. Therefore, when I say z plus s is greater than 0, from this integration what I mean is real part of z plus s is greater than 0. That means real part of z plus real part of s is greater than 0. What is the real part of s? Sigma. This real part of z you put as it is, greater than 0. Therefore, sigma is greater than real part of z, minus, because if it goes to the right hand side, then it becomes minus. Maybe I will work out neatly here. Z plus s is greater than 0. Then we, as I said, we always worried about the real part. Therefore, you take real part of this. Real part of z plus s must be greater than 0. So real part of z plus real part of s must be greater than 0. So real part of s must be greater than minus of real part of z. That's it. Therefore, when we have a function e power minus zt times u of t, then its Laplace transform is 1 over z plus s, and the ROC is real part of s must be greater than minus of real part of z. That's it. So the ROC is very, very important. If you don't mention ROC, then there will be problem. We will work out a problem and we will show you. For example, if you take e power what can I say? Okay, I'll come to that little later. So once we have this relation, we can find out the Laplace transformation of trigonometric functions. Like if I have cos omega naught t times u of t, then this can be written as 1 over 2 e to the j omega naught t plus 1 over 2 e to the minus j omega naught t u of t plus 1 half e to the minus j omega naught t and u of t. Okay, now what is this? This is equal to, you put 1 half as it is, and this part is equal to 1 divided by s plus j omega naught, no, omega naught t, I am sorry, omega naught t. Okay, plus 1 by 2 divided by s minus omega naught t, omega naught. Now you bring out 1 half commonly outside, then s minus omega naught plus s plus omega naught divided by s plus omega naught times s minus omega naught, therefore s squared minus omega naught squared, and this omega naught and that omega naught will get cancelled, 2s and this 2 will get cancelled, so therefore this is divided by s square minus omega naught square. Simple algebraic manipulation. Similarly, if the same kind of steps if you follow, then the Laplace transform of sin omega naught t becomes omega naught divided by s squared plus omega naught squared. Okay, so in this derivation, the abscissa of convergence should be the real part of z. Okay, if you take this one, then what will happen? 0 to infinity 1 half e to the j omega naught t times e to the st and dt, right? So if you work out this, then 1 by 2 integral of e to the minus st minus of s minus j omega naught times t and dt. So 1 by 2 e to the minus of s minus j omega naught I am sorry, this j term will come here, this also j term, therefore s square plus omega naught square. So plus here and here also plus, thank you. So this is again plus. Okay, so then substitute the limit 0 to infinity. So in order to converge, this factor has to be positive. So s minus j omega naught must be greater than 0. That means what? The real part of s minus j omega naught must be greater than 0. So real part of s minus real part of j omega naught must be greater than 0. What is the real part of j omega naught? It is 0 because there is no real part in that. So real of S must be greater than 0. What is real of S? Sigma. Sigma must be greater than 0. So the region of convergence is, this is sigma and this is omega. So entire right half S plane. So for these two, sin omega naught t and cos omega naught t, Laplace transform of this. For both the guys, ROC will be sigma is greater than 0, and here also ROC will be sigma must be greater than 0. That's it. Okay. So now we can represent poles and zeros of this Laplace transform in the complex frequency plane. Okay. These are all rational functions of time. Like therefore, poles and zeros exist for this. As far as del of t is concerned, it is 1. Okay, it has no poles, neither poles nor zeros, no poles and no zeros. So therefore, in the entire complex plane, this is sigma and this is j omega. No poles, you cannot draw, no mark anything in this. But as far as u of t is concerned, there is a pole at the origin, because u of t, if you take Laplace transform, then it is 1 by s. What is the pole here? S equals 0. So pole will be marked by a cross like this. Okay, and then we considered e to the minus alpha t times u of t, and what is the Laplace transform? 1 divided by s plus alpha. Therefore this guy has a pole at minus alpha. Similarly, what is the cos omega naught? Cos omega naught times u of t, if you take Laplace transform, then it is 1 by 2, 1 divided by s minus j omega plus 1 by s plus j omega. Okay, so it has two poles, they are complex conjugate, one is plus j omega and another one is minus j omega, sigma axis, omega axis. Okay. So there are two poles. Okay, let me stop at this point, and again I'll bring with some few more examples in the next lecture. Thank you very much.